So our first presentation for this webinar is designing grounding systems that safely dissipate both fault currents and lightning current. This is presented by Steve Weber, who's a senior engineer at DEHN Corporation, USA. So Steve, the floor is yours.
Thank you, Dan. We can move on to the first slide, please. So just first of all, thank you for everybody joining, and thank you for having Dan been involved with the SPEC webinar presentation. I think it's a good opportunity for us to share and discuss good knowledge. So a couple of contents that I want to cover in this presentation is basically looking at the grounding system performance from a power frequency fault perspective versus the performance of the grounding system, looking at it from the perspective of injecting lightning current or lightning impulses. And in doing this, we're going to look at a few scenarios where we're going to compare human safety step and touch voltage comparisons, and also discuss what is the mitigation techniques that we implement to address lightning and surge injection into the grounding system to try and mitigate touch and step potentials that arise from these injections, causing very high ground potential rises and ultimately could damage equipment or result in danger to human life. Next slide, please. So first of all, to the right, the picture on the right, you'll notice a sinusoidal waveform. And first and most important thing that we have to realize is that power frequency is basically one single frequency where power is directed through the groundings of through the power system and into the grounding system. And in the US, we're looking at 60 hertz, and in other parts 50 hertz. But when we look at lightning impulse current, it's basically a impulse that has a very, very short rise time, denoted by the T1 value that you see on the graph on the left, and then a very fast decay time. Normally these values for these impulse currents are a rise time of about 10 microseconds for when we consider lightning waveforms according to IEC. And that means that it'll rise from 0 to 100% or its peak value within 10 microseconds, and then decay all the way down to 50% of its value within 350 microseconds. So appreciate the fact here that we're looking at impulses and that occur over very short periods of time. So we realize that this is also defined as a Heitler or an exponential function, because of the fact that it rises exponentially and decays exponentially. So what the guys, Professor Meppelink, and you can see the paper that was written down there, the calculation of lightning effects in the frequency domain, which Professor Meppelink and the creators of the XGS Lab software did, is they determined what would be the frequency for a representative sine wave that would have the exact same rise time of a lightning impulse. And you can see there to the right that is estimated to be a 25 kilohertz sine wave. So first of all, lightning dust is a very high frequency phenomenon. And then in the table to the left, you'll notice there that I've shown three different strokes that occur. First of all, you get your first positive stroke, which we don't really see all that often, having an equivalent frequency of about 25 kilohertz, and then a first negative stroke having a equivalent frequency of about 250 kilohertz. So appreciate the fact between power system frequency and lightning impulse. So this will basically determine the input that we're going to consider in the rest of the presentation. So next slide, please. So first of all, touch and step potential. We're all engineers, we all understand this, but just to get the terminology in place, we all know that touch and step potential is the direct result of the ground potential rise that we see on the grounding grid. And the ground potential rise obviously is a fact of, or is a factor calculated from the fault current and the grid resistance. And there are other factors that also come into play, like the the physical design of the grounding grid, the soil resistivity, but it comes down to an injected current that goes into a specific grid resistance, resulting in a certain ground potential rise within a soil resistivity layer. And ultimately, we can have a touch and step potential on the surface of this grounding system that could exceed certain allowable body limits. Next slide, please. So to control and mitigate these risks, we obviously ensure that we have the grounding resistance as low as possible. We create, very important, an equipotential plane when we design these grounding systems. And remember, these mitigation and control, these mitigation of the risks of GPR is relevant both for power system faults and lightning current, because we need to ensure that the grounding resistance is as low as possible. And we need to make sure that if you either the fact that you inject a power system fault or lightning current, we have to ensure that we create an equipotential plane over the feet of a person standing there, so that there's not a big potential difference between the legs, and thus we don't exceed the calculated current limit that can actually flow through the body. And like I said, the grounding resistance is dependent on the grid shape and the soil resistivity value. So moving on, when we look at lightning frequency and what is the ground potential rise that we can consider for lightning frequency, we can see that lightning, first of all, has a very high frequency behavior. And I just showed you a equivalent sine wave calculation that was done for the hydro functions that we have for lightning impulses, that it can range all the way from DC all the way to 10 megahertz in frequency. So this lightning impulse actually is comprised of different frequency components. And this GPR steepness that we witness when we inject lightning current into a grounding system is obviously increased with the frequency. So a high lightning current that we see for the different levels of lightning systems also contribute to the high GPR levels. And in the tables that you see there, notice that I've divided it into the 4 levels that we normally see for the IEC 62305 systems. But you can see that generally you're looking at 100 Ka, 150 Ka, and then in practice, in real life situations, they might be smaller than this, but it's always within the thousands and multitudes of thousands of amps that is injected into the grounding system. Obviously, at these high frequencies, with these high current levels, it results in these high steepness GPR curves. Next slide, please. So when we consider injecting lightning current into our grounding systems that we design and verify, the first important thing that we have to realize is that 90% of the lightning strikes that we consider across the world in terms of the probability of existence is not first negative impulse lightning strikes. So if we look at the table there and the parameters for a first negative impulse, you'll see there that there's a different waveform that is defined for simulating these lightning strikes. And yes, it does differ from the 10-stroke 350 microsecond test waveforms that we have for components and for surge protection devices. But these values, as they are in IEC 62305 Part 1 and one of the annexures, really gives a good base value for the lightning impulse waveforms that you can see, waveform that you can also see there on the right as the input in calculating these GPRs. Next slide, please. So a grounding system that is safe of power frequency and it's not safe for lightning current or lightning impulse current is considered. So we have a grounding resistance of this example that we've done that you see there to the right that basically gives you 10 ohms. A soil model that's calculated to be 2 layers, and we've not added any surface coverings. The lighting creates a steep and large GPR around this building. If we inject this exact same grounding system with the lightning current, it would definitely not be safe for touch and step potentials, but it would have been safe for a power frequency ground fault. And obviously these voltages now pose a significant risk. Next slide, please. So when we talk about the allowable or the tolerable limits for power frequency, these are all calculated based on the IEEE standard 80, where they define a 50 or 70 kilogram person and you can calculate what would be the tolerable limit for step and touch potentials. But in the case of lightning, there are actually a few theoretical research papers and standards have different values that they have defined for what is considered a safe tolerable limit for step potential. So for the purpose of these calculations, we use the IEC 60479 value that you see there of 25 kV for a person's with a 1 meter step distance as the tolerable limit for calculating these touch and step voltages. And then I've got a picture there of a person that we have to also remember that just by insulating a down conductor does not really make it safe for a touch potential. Even if the conductor is insulated, we still have a conductive loop or a mutual inductance that the human body creates because it's also conductive. And this spark over voltage could exceed the insulation value of that down conductor, and it could result in flashover as well. So this being our tolerable limits and the waveform that I've shown previously as the input for that example grounding system, we can move forward. And you'll notice that same grounding system now receives a lightning protection system with air termination rods, down conductors, and you can see there where is the injection point where lightning is injected into the air termination rod. And to the right, it basically resulted in very high uncontrollable touch voltages if we consider injecting the lightning current into this grounding system. So in other words, a grounding system for a substation or a building or even a public place like a school or something like that would have been safe for the power system faults. But the moment we install the lightning protection system to it, we consider the fact that it's now subjected to lightning current, it does change a bit in terms of what is safe in terms of touch and step potentials. So moving forward, there's a couple of things that we do to reduce these touch voltages. So the IEC standards and the the NFPA standards as well, talk about swirl covering material that we can use around the down conductors. We can install warning signs. We can even keep the down conductors in places where they're not really accessible for persons. If we increase the amount of down conductors coming down the system, that could also reduce the risk by dispersing the lightning current throughout the grounding, the lightning protection system. And we can, there are a few marketed down conductor systems that are insulated, that have insulation that can actually withstand the voltages that we can see for a person touching it. Moving on, you can continue. And then, of course, like I said, surface covering layers, which increase the resistance between our feet and the ground potential rise that we see, we can also use. So this is also a mitigation method that we use to try and reduce the step voltage for persons in these areas. Moving on. A very important thing that we also started using is what we call these concentric rings that we have around poles, power fields, sport fields, where you have your lighting and even radio towers that are in populated areas. We start installing these rings that provide a voltage control by reducing the steepness of the GPR in the grounding system. And that also makes it easy, makes that equipotential plane better, so that you don't have that steep gradient and a big potential difference over people's feet. And that would result in a safe step potential situation. Moving on.
Steve, just so you know, you're down to about 2 minutes.
Okay, thank you. So initially, like I said, there was no consideration for lighting in the design for this system. And you notice there that it results in a very high ground potential rise steepness. And obviously, like I said, if a person stands on that gradient, he's exposed to very high touch and step potentials. So this is initially what the system would have looked like if we injected that lightning current impulse for that value. And you can see it's a very high GPR potential values. And that's all because of that high current and at high frequency. Moving on. So like I said, modifying the grid layout to control this GPR, installing these rings over, in high populated areas around the structure, and, especially in the case of lightning shelters, you can install these rings at different depths, like I said, and moving outwards. And in the next slide, you can see that ultimately resulted in controlling that potential. That results in a equipotential plane. Yes, it's still a very high voltage, but the voltage considering across a person's 2 feet would be significantly smaller and result in a safe step potential exposure. Next slide. And that just again shows from a top view, if you do these rings around the structure, how we control that equipotential plane. And you can actually see that it really results in a much smaller or much bigger area of the equipotential plane where persons would be safe. Next step, next slide. One thing that I want to mention is all these graphs are done with a simulations that we do in the frequency domain. And considering the fact that lightning is of different frequencies, we actually have to do these simulations in what we call the time domain, where we define the calculation in a line across the grounding grid that results in different potentials for each frequency, and then ultimately would give you this line curve that would show that it's still within the tolerable values if you do the simulation in the time domain, because it's a lightning impulse. So I've done all these in the frequency domain as a good representation to do a check for the grounding system. Next slide. Yes, and that basically concludes my presentation with a conclusion that, a lightning current impulse results in much higher ground potential rises, much higher steepness in the ground potential rises, and that could also result in unsafe touch and step potentials. And then we mitigate these by implementing the swirl covering layers, by implementing different designs for the lightning protection system, as well as swirl covering layers, and as well as these rings that we install at different depths across around the structure. Thank you for your time.
Thanks, Stephen. That was a great presentation.